everyone. This is Jeff Wilkerson, Professor of Physics at Luther College, with an introduction to thinking about why we might sometimes want to graph the logarithm of a variable, the logarithm of a dependent variable, instead of the variable itself, when we have exponentially related data like we might in an RC timing experiment like we'll be doing in the General Physics Lab 2 laboratory coming up here. So if we have an expression that looks like this, we could just make a graph of I versus t, and we would expect to see a exponential decay of the current with time. And that's going to look, I as a function of t is going to look something like this. Okay, that's great. And our ability to fit relatively complex functions to curves like this, curves to data like this, is significant, and we could fit an exponential function. We could go right into Kaleidograph, for example, and fit an exponential function here and do a great job. If, however, we take the logarithm of both sides of this, let's see what happens right here. If we take the logarithm of both sides of this equation, we end up with the logarithm of I on this side, natural log of I. Natural log of a times b is natural log of a plus natural log of b. The natural log of a is natural log of the initial current in the circuit. And then we have the natural log of e to the minus t over tau. And the natural log of e to the something is just that something. So this is minus t over tau right here. We now have a linear relationship between the logarithm of I and the time. And so we can write this as, we can graph this, the log of I versus time, and we would expect to get a line out of here. And this is an equation of the form y equals mx plus b, our typical linear format like this. So the slope of this line looks to me like it's going to be, the intercept looks like it's going to be the logarithm of the initial current, and the slope looks like it's going to be negative 1 over tau. Now, our brain's does a little bit better job of understanding linear equations like this and seeing a steeper slope or a shallower slope, what that means in terms of our tau, RC, in this RC timing circuit. And so our brain likes to see these linear graphs and to see these relationships and to do that. But even more importantly, so this is the way I would analyze this data. Despite the fact that I could do a good job of exponentially fitting this, I can do a good job of linearly fitting this too. So I'm going to do a linear fit to this and measure the slope, and that slope's going to tell me what my RC is. And if we've measured the R, well, then we can measure the C as well from that, the capacitance in the circuit. So this is all great. This is the kind of thing, this is a good way to go forward with doing. Now, we could get that out of the parameters of the functional fit right here. But one value of this, for example, is that, of course, we can determine the uncertainties in the parameters of fits when we're doing some sort of multivariate regression. But it's easier for us to determine the uncertainty in the slope and the uncertainty in the intercept in a linear function, a linear fit like this. So when we have a fit of this form, we can say that the uncertainty in the slope is just the 1 over the number of points that we have right there times the sum of how much we missed. This is the square of the deviation of how much each point missed our linear fit. So for example, you've got a linear fit that looks like this. You've got a point that's down here. Your data point is here. Your data point is here. Your data point is here and here and here and here. And you can measure the deviation of the fit from each data point. You square it so that it gives you that's a scatter. It's not, they don't cancel each other out, a negative scatter and a positive scatter. So this is your data point minus what the fit predicted it would be. So this is measuring sort of the average deviation of the fit of the scatter of your data from your fit, and then times this term that measures this is the number of points that's in here again, and so this is the sum of the squares of your x values minus the sum of your x values squared. So you think about your scatter there, this sort of, never mind what that is, but this is the way we can start to think about this. This is relatively straightforward for us to do. We can plug this equation right into kaleidograph, for example, and boom, we can determine the uncertainty in our slope, and we can get the uncertainty in our intercept the same sort of way here. And so this is a very, very valuable thing for us to be able to do, to say, what is our uncertainty in RC? Can we plug this in and get this uncertainty in the slope, which is going to give us something of an uncertainty in our capacitance values that we can start to look at and start to do this kind of calculation, which is much easier for us to do than if we tried to do an exponential fit to the data up here. So that's one of the reasons we want to take the logarithm and plot the logarithm of the current versus the time versus plotting the current versus the time, which you could do both. It's easy enough to make these graphs. You make a column and you have the current in one column, then you just take the logarithm of that value and put that in the next column, and you can try both of these graphs both of these ways and see what you get that comes out of there. So this is what we kind of want to do, and maybe we can push forward and try this to see if we can do this sort of calculation to understand what our uncertainty in R and C is. This data, we should point out that this uncertainty in the slope and this uncertainty in the intercept is built on the idea that we have negligible uncertainty in X, for example, and that each of these points is weighted the same, that we have the uncertainty in each of these data points is the same. If one of these data points is wildly uncertain, we don't want to weight it in the fit as much, and we don't want to weight its deviation from the line as much. So we have some assumptions that are built into this idea. Our assumptions that are built into here say, this is only works for us if we don't have, if the uncertainty in our x values is small. Okay, if our uncertainty in the time values here is really very small, then we can get away with doing this. And if these data points are all sort of equally likely to miss the line, then we can get away with doing this. Otherwise, we have another approach we could do, but we're not going to get into that right now. We can talk about that later. So this is what we got. This is a way to think about the uncertainty of lines, of the linear fit parameters, the slope and the intercept, and a reason to think about this as a way to analyze our data when we have exponentially related data. So very quick introduction to a way to think about processing the data from an RC timing experiment. Thank you.